first. Well, we're actually continuing the mini.
How do I get rid of that?
Got it.
I got it. Very well.
Remind something.
Right. So in the a couple of days ago, I tried to explain that now we know how to compute Hausdorff dimension of some Gauss contour sets, which defined in terms of continued fractions of the elements. And I also tried to explain that this problem is connected to the study of Markov and Lagrange spectra, which are two very intricate subsets of the real line, and they have been studied extensively for the past 150 years. And they managed to unravel some structure in the sets using basically computing Hausdorff dimension of a lot of sets of continued fractions. And last time I explained that how to deal with a case when you don't have any restrictions. So basically your iterated function scheme is Bernoulli, and there are no extra complications like one digit cannot be followed by another one and things like this, which makes the iterated function scheme much easier. And okay. But this was also done in particular by Hensley, and in some sense we just made we got more digits, and we strictly proved what his estimates were. But now we are moving to completely new fields, something that was completely beyond, completely out of reach before. And in particular, so last time I also set an approach to estimating Hausdorff dimension of the Markov spectrum in half line. And this apparently turned out us to the problem of computing Hausdorff dimension of this set. So the connection was first drawn by Bambi about 50 years ago, and but that was where the state of art was then. And
these are forbidden words?
Yes, these are forbidden words. These are forbidden words which apparently show up if you want to compute Hausdorff dimension in the approximately to 1/3 from 3 and 1 to 3 and 1/3 to 3.333. Yes, so this forbidden words that show up, and so our business more or less now is to see how we can accommodate complicated things like this. Right. So that words were much longer. So let us just see the principle with a simple example. So I assume that we want to forbid only 2 strings. So it means that 1-to-1 are not allowed and 2-1-2 are not allowed. So only that everything else is possible. So by the way, if you just remove extra digit and you remove and you add a restriction just 1 and 2, then your contour set becomes just 2 points. So it has a Hausdorff dimension 0. But this is maybe the first non-trivial example. And for this, you'll get an iterated function scheme of 4 maps. And So, and with a Markov matrix like this, so each map is corresponds to is just composition of two branches of the Gaussian map. It looks like this, and this is the Markov matrix, which tells you basically is that so each line in this matrix and each column of this matrix, they are indexed by words of the length 2, like 1, 1, 1, 2, 2, 1, and 2, 2. And for example, this one means that 1, 1 can be followed after 1, 1. And this 0 means that after 1, 1, so 1, 2 cannot be followed by 1, 1, because then you get combination of 1, 2, 1, 1, and this is not allowed. So this Markov matrix basically tells us which map can be applied one after another. And since this condition, which is written here in mathematics, so that the element of matrix is equal to 1 if and only if this combination of the indices doesn't contain neither 1, 2, 1 nor 2, 1, 2. And of course, if you have much more longer words, then your matrix is going to be, rows and columns are going to be indexed by combination of words of length n-1. So it is going to be a matrix of the size 2 times n-1 by 2 to the n-1, and the size grows exponentially. And here's the limit set. Limit set is exactly the set of Gauss counter set on a real line. It has counter structure. It can be obtained from this iterated function scheme with this matrix. And basically, you just take any point and apply iterations on the map so that the sequence of indices in our iterations, it doesn't contain any forbidden subsequences. So this is and this corresponds exactly to the set of digits whose dimension on this occasion we are interested in. This seems to be very simple. But this two example, it came from an actual paper by Gustavo Moreira and by Carlos Gustavo Moreira and Carlos Mateus Santos. And they were studying the difference of the Markov and Lagrange spectra. And in their paper, they wanted to know, they didn't actually know particularly what it is, they just wanted to know that it is bigger than 3.65, because they were interested in estimating the difference of the dimensions. This paper is a bit difficult to read, but it is full of questions like this. And why is this? Well, because it turns out that the set difference in different intervals, it constrains this counter set as a subset. So the dimension of our counter set that we were interested in is actually gives us an upper bound on the dimension of the set difference. Yes, I think I'm correct. Okay, so and then we started producing all these bounds. They were coming like presents from the Christmas box. So we were able in a matter of a few seconds to do in a matter of a few minutes to do basically all of them. And so we obtained much sharper bounds on the dimension of the set difference between Markov.
Is m minus n is one is in definition with soup, one is with soup.
Well, it is not empty because it actually contains a set E2. Yes, it contains a set of all continued fractions with digits 1 and 2. So,
M minus L?
yes. So this is one of the first results, that it contains the M minus L, it contains a set which is...
The definition supremum?
Yes. It is limits of... Yes.
That means that some sequences in one of them has no task. Because
They look okay, Lagrange spectrum belongs to the Markov spectrum, and you can construct, and one can construct counter sets of continued fractions which are sitting in the difference.
Difference is what?
Supreme, so
maybe supreme is infinite going back.
Supreme was infinite going back, and that's what I was talking on limit soup. Yes. Yes, and yes, so that's it's and one of this Gauss counters.
Bigger set.
Yes, yes. Yes. Yes, it doesn't see the past. Yes, so that, and one of the first sets that they constructed in the set difference was actually homeomorphic to the but just the E2, so it is just a set of all continued fractions with digits 1 and 2. So it is just it's just sitting inside.
Go on. These are only two degrees and bounded.
Yeah. Okay. The height is, yes, okay, at least. Okay. So what we need, what we need is that we need to introduce to define our transfer operator again, but this time if we do it with a Markov condition, and then the system becomes much more complicated, and we, in addition, instead of looking at the space of functions on just one interval, we have to multiply, we have to take several copies of the space of functions, and we define now a bounded space as the card product of several bounded spaces, and now the transfer operator on a space of this now twice differentiable functions, they actually can be taken analytic, is defined exactly with this taken Markov condition into account. So instead of just one map on an interval, we have maps, so maps acting on the direct product. So a few copies of the unit interval with the length of the alphabet. And then if you take So, and fortunately, on each of the copies for our system, our map is defined the same. So it is just taken to its own copy. So all copies are just taken to the same interval, so the images are the same, and just map. And our transfer operator is taking Markov matrix into account, meaning that this take derivatives of the case map and multiplied, so that it is affected. This case map is affecting function number j only when mgk is not zero. So this is now acting on a space of functions on this Descartes product on this disjoint set of intervals, and the function on the interval number j is affected by the map number k whenever the matrix Markov matrix is not zero element there. And of course, we can play the same game as before, except that now our space of functions is much more complicated. So, okay. Okay, because instead of just looking on one space and constructing just one polynomial, we need to construct a lot of them. But at the same fact, the Bowen lemma still works for us because our system is still hyperbolic. So what we can do is that we can just multiply, take several copies of our initial data and play the same game. So we take now Chebyshev points in all intervals, and Chebyshev polynomials in all intervals is Chebyshev Chebyshev points in all intervals with Lagrange polynomials, defines that. And now what we want to do, we want to define now our matrix, which is going to be again finite dimensional approximation to our operator, constructed in a special way. So it is constructed by evaluating again transfer operator applied to our basis functions, our Lagrange polynomials, and evaluated at the Chebyshev points. Why? Because then we can, it is just a projection on the space of the basis functions. And this is now a very large matrix of the size, which is of much bigger size. So our idea is the dimension of the system, and it can be just guessed to the number of maps we need. And this is our matrix, which is basically obtained by taking the matrices. It consists of the blocks of matrices with elements of the Markov multiplied by the elements of the Markov matrix. So that for every non-zero element of a matrix, we set here the matrix which is coming from the evaluation of our operator on a particular Lagrange polynomial at a particular Chebyshev point. Okay. Okay. So I keep just, so your question is running in my head. Let me just say that you can construct.
I don't remember definitions.
You can construct explicitly Gauss counter sets which are sitting in between. Okay, so maybe I will not worry about it for now. And okay, and then by taking again the eigenvector of this matrix, now we can reconstruct the functions that we are interested in. So there is nothing very new here, except that Markov condition or introduction of this makes our system much larger, probably also much more interesting to deal with. And so this where the main difficulty was actually line for a very long time, probably that when you have a system of like 2 to the power 16, for example, maps, computing periodic points is just hopeless. You will not get very far. And here we try, instead of computing this going long way, we're trying to reconstruct the eigenvector. For this, we are taking a projection of our matrix on the space spanned by polynomials, and projection is actually operator of evaluating a function at Chebyshev points. So probably I should have written it here, but I didn't. So the idea is that there is a unique correspondence between a sequence of between the values of function at these specifically chosen points and the composition of a function, an approximation of a function in these bases. So if we know the values of the function at the Chebyshev points, these are our coefficients in the basis of Lagrange polynomials. So it is this is just a projection operator and functional analysis. So, but instead of considering the evaluation, it is evaluation functional in some sense. Okay. Now, of course, with such huge matrix, we are facing obvious problems. Fortunately, we're trying to compute its eigenvector, but fortunately for us, we don't need all eigenvectors. The computation of all eigenvectors would have been unstable, but we just need one. And to compute one single eigenvector, you can just use the power method and take any vector you like, for example, vector consisting of ones, and apply your matrix over and over again, and it will converge to the maximal eigenvector that you need. So here,
Thanks about that. Usually you need diagonal dominance or something to get the power method to converge quickly. You need some structure in the matrix. No way, but I don't know what the spectrum looks like, so it'll get good converting.
So we don't. I really don't. We don't have any kind of dominance here. All we have here is that the operator preserves that we know from the Bohr-Rel theory that that any positive function converges to the eigenfunction. And our operator matrix is coming from approximation of the operator on this basis. So this what saves us is convergence is exponential fast. So we take a vector consisting of just ones, and which would be representing some positive function, and that's why power method just converges. Okay, And then the problem here, of course, is that it is still sort of large. And if you just try to do simple approximations, that if you take n equals 17, that means that your condition, you just take the strings, the exclusion strings of length of 17, and then your Markov matrix will be about 2 gigabytes in space, and this is just 2 gigabytes of zeros and ones. And if you try to do more than that, then it comes to about 1.5 terabytes, because if you try to work with a real matrix. So because if our matrix is not of zeros and ones, it has some jitters in it from evaluating of that operator, and this is looks, yes, okay, and this is
compressed sensing.
no, some mathematics instead, some mathematics. Well, okay, it will come in a second. This is again looks a little bit hopeless, because you're not going to be able to compute an eigenvector of a matrix if it is 1.5 terabytes. But what you happen to notice, and that actually you don't need all metrics, because your Markov matrix has a lot of identical rows and a lot of identical columns. And this comes from the fact that the strings that we have to deal with are very long, and there are not too many of them. And basically, what happens, the rough estimate on the number of different columns or rows in the Markov matrix is just the number of different tails in U set of forbidden strings. And it's an upper bound. It can be a little bit improved, but it is even a good estimate already. So, for example, if you have just one condition of, and it will be just one word of length 24, then it has only 23 different tails or different heads. And therefore, your Markov matrix will not be, to store this information, you don't need Markov matrix of the length of the size 2 to the 23. All you need is just a matrix of the size 23. So the claim here is that, fortunately for us, you don't need to keep the entire matrix itself for this type of problem. Here you just need to remember which rows and columns are the same, and the actual and keep only the different information about the different one. So, and this is a great saving in memory. In practice, it also means that our eigenvectors that we are looking for is in a much smaller subspace. So we had, like, for example, 4 millions of columns, but the eigenvector that we need has only a dimension of 429. And of course, working with a matrix of the size of 400 is entirely possible. So this we can recover eigenvector, eigenfunction just from very little information. So we don't need all of it, just because a lot of it is the same. And so this is yes, and the entire matrix that we have to deal with has a size about 4,000 at the end. So this simplifies things quite a lot, which allows actually to carry all these computations. Okay, any questions? Okay, so this is, I think, summary of what we can do. Also, for summary of the first part, which was called computation of dimension. So we managed to finally establish the transition point for the dimension function. We computed actually the estimate on the side difference. This lower bound is coming from the set E2. This is Hausdorff, which is sitting inside there. And this upper bound is coming from our estimates of the Gauss countersets. And actually, I'll find a few points sitting there. Yeah, we finally managed to compute the dimension function. This is the end of the first part, which may be a good time to ask questions. Shall I go to the second part now? I can ask a question. Okay.
All right.
Yes.
My question is, so what are the main open questions remaining in this topic?
In this topic, well, we still cannot bring it up. So, for example, we don't, so that there's still quite a gap in these dimensions, so that we don't know how to deal with this. What also we don't know, well, we don't know, for example, this problem is tightly connected with the question of the sum sets of the counter sets. So that we can still ask whether it is true or not that E2 plus E4, for example, contains an interval. So that there was the mentioning of a result of Hall before, and the question which is really remains open, that if you take just a sum of two Gauss countersets, it is so for some of them. It is known, for example, that E4 plus E4 contains an interval. So if you take, that means that if you have a unit interval, then any number can be represented by a sum of two elements of the counter set if with digits only 1, 2, 3, and 4. But for example, the case of E2 plus, but how small this set can be, we don't know. We have reasons to believe that if it is that because at least my coaches were insisting that because the dimension of E2 is bigger than a half, then E2 plus E2 also should contain an open subset of the real line, but we don't know really. So this type of questions remain. Maybe does it answer your question?
Yeah, but I wonder for the difference between M and L, is it mostly a mathematical problem, or can you improve the estimates by taking much more powerful computers?
No. So the problem is that we actually don't know that. Okay, we don't know how to construct these counter sets which are sitting in between. So that was like a breakthrough when they realized that you can fit this one set, but really we don't know how to do that. There is no algorithm for that at the moment. Okay. So the plan was to go to part 2, which is called dimension of a measure. I don't know if we want to have a break now or if we want to take a break later.
Yeah, I think it would make sense to make some break before the.
Okay.
And let's.
Going to change. Oh, so we're going to change the setting again, and now instead of looking on a problem in number theory, I'm going to look on a problem from probability theory. Okay, so what is the question? The question is the following. So the question concerns special measures, special probability measures on a real line, and they're defined in the following way: that we take just consider the sum of speaking number lambda, and consider the sum with infinite sum of the powers of lambda, where the signs are alternating at random. So this is perfectly well-defined random variable, and we can assume that for simplicity now, within the classical setting, that the signs, that every sign plus and minus is chosen with equal probability of a half. And they are chosen, of course, independently, like by the coin toss. And the distribution, this probability measure, which is defined by this series, by the law of sigma, is called Bernoulli convolution. So our task today, today I'd like to discuss the properties of this probability measure mu lambda, which is basically the distribution of this random variable C, which is defined as a power series of this randomly chosen signs. So first thing, of course, the sum is somewhere in the interval from 1 over 1 minus lambda and 1 over lambda minus 1 and this is just because if you take all signs the same, this is what you get. This is geometric series. So no surprises. So our measure is going to be supported somewhere on the interval from minus 1 over lambda and 1 over lambda. Okay. So it is convenient for us just to make a translation, and instead of considering a variable on the interval symmetric with respect to 1, with respect to 0, we're just going to make a shift so that everything is the interval 0 and 1 over lambda, and it doesn't make actually any difference for our purposes. But now we can have dynamical interpretation of the thing. So, and we know that the variable that we have, it obviously satisfies this relation that you can we can consider we can separate the first term, and then this inequality holds, which actually means for us that the measures that we are considering actually a stationary measure for this system of the linear maps of an interval, and where all maps are taken with equal probability, 1/2 and 1/2. And then the station, what does it mean that the measure is stationary? It means that it is satisfying these relations. So that if you take induced action, weighted induced action by two maps on the measure, then this equality holds. So once again, we started with the measure which is defined in terms of the distribution of some random variable, and for us to get it back to our lens that we know and love, we just make simple observation that it is actually a stationary measure for this system of contractions of the real line. Yes.
Times on the definition of
Yes.
C is equal to 1/2.
Yes. Yes. Okay. And of course, in this setting, the stationary measure is unique. So let us just think a little bit what we can say about this measure straight away. So if our lambda happen to be smaller than 1/2, then it is going to be supported on a counter set. Indeed, then the images under these two contractions, they are going to be disjoint, and the limit set is just a counter set of on a real line. It's not very interesting. So in particular, if you choose lambda equal to 1/3, it is a middle third counter set that we also know very well. But if your lambda is equal to 1/2, then your limit set is going to be, the measure is going to be supported on the interval, and is actually a Lebesgue measure. And the most interesting case is, of course, when the remaining one, when lambda is bigger than 1/2, and then this is the measure is supported on the interval between from 0 and 1/1 minus lambda. And now we want to know more about it, or we can ask more questions about it. For example, it is supported, okay, on the interval from 0 and 1 minus lambda. What is it relation? Well, how is it related to the Lebesgue measure?
The same question as this convolution of harmony.
Yes, this is it. I started. The measure is called. Yes. Oh, sorry.
Is that quite what is in the question? Yeah. Okay. Is there a formula?
Yes, we started with it.
Okay.
Okay.
I didn't.
Okay. Oh, very well. And it turns out that apparently this depends on algebraic properties of our parameter lambda, and depends on properties of parameter lambda very heavily. Okay, so like I cannot do anything without looking at it. First, so what I did at first place, I thought, okay, I'm interested, I would like to know what the measure is looking like. It looks like. So maybe what we can do is that we can take a very, very fine partition of the unit interval. Here we took it into 2 to the power 16 small equal intervals, with you or not. And I computed the measure of each of these 2 to the power 16 intervals, just measuring how much how often my random variable lands into this interval, and this is what I got. So what is shown on this picture? So actually there are 2 to the power 16 dots, if you could count them, and each dot corresponds to the measure of the interval which is sitting above. So because of the scale we are, 2 to the power 16 intervals fitting there looks like would look like a dot. dots basically, and every point on this picture is just a measure of the corresponding interval. So, for example, one can see that apparently the interval hanging somewhere in the middle it is also the scale. So somewhere in the middle has the highest measure. So most points, most of the time, my random variable is somewhere here. And then there are another distinct points where it seems to be tends to go, but there is also gaps. So some intervals it doesn't like much, and things like this. And overall, this is very typical picture. What you get if you try to plot the measure which is singular with respect to the Lebesgue measure in this way. And it is fully supported on this unit interval. So each interval has each small interval will have non-zero measure, but it is looks completely chaotic. So it isn't very informative.
Self-similar.
It's self-similar, yes. Yeah. So as I pointed out that there is a lot of algebraic properties of the parameter going into it, and one of the particular classes of algebraic integers which appear here is called Poisson numbers. And Poisson numbers are just algebraic integers bigger than 1, so that all its algebraic conjugates are smaller than 1 in absolute value. Yes, but I cannot pronounce the second one, so I'm just calling them with Poisson numbers. Okay, so this is our polynomial, and we want that this is our lambda. It is a root of polynomial with the integer coefficients, and all its algebraic conjugates are smaller than 1. So one of the most famous examples is the golden ratio. So it is the root of the polynomial of this one, and let me just try. It's going to be a lecture. So can you guess this? What would be approximately the phi to the power 100 if you say like with an error of 10 to minus 5?
Question?
Oh, the question is that you have a golden ratio and you raise it to the power 100, and we want to know how big it is. If I tell you that I want an error of 10 to the minus 5.
100 Fibonacci number up to some point.
Well, somebody, okay, it was a joke. It's not a much joke, but any guesses? Okay, let me continue then. So the claim is that fractional parts just converge to, so fractional parts converge to 0 as k tends to infinity. And so it is just, okay. So the fractional parts of the Fibonacci numbers converge to 0, and this is very easy to see. So if you take just the expression of k's, the sum of k's powers, then we will see that this is a symmetric polynomial in the roots of with respect to the roots of the minimal polynomial for the Poisson number, and it can be written in terms of the coefficients. The coefficients are integers, so these guys they are smaller than 1, so they tend to 0, and the only thing which remains is going to be this one. But it also has to be integer numbers, so it converges to 0 rather rapidly. Okay. And apparently this fact was used by Erdős, who made one of the first contributions to this problem. And he proves that if the measure is the lambda is a Poisson number, then the measure is singular. And here now it is going to become clear why the measure is called Bernoulli convolution. It's because, in fact, it is a true Bernoulli convolution. So it can be written as the same thing as an exercise, that it is a convolution of Bernoulli variables, of scaled Bernoulli variables, which are sitting in the points plus minus lambda to the power j, and therefore, if one can take Fourier transform of this measure, and when you take Fourier transform of a measure, it becomes product of Fourier transforms of the components, and then Fourier transform of a component is just Fourier transform of this Bernoulli measure. And this one can be computed explicitly, but if you are not, it is just cosine of 2 pi t lambda to the power j. So if our lambda is actually Poisson number, then we know from the previous slide, hopefully, then that lambda j, they actually converge to integers very quickly. They converge to integers very quickly, and therefore the values of the Fourier transform along this sequence, they're not going to converge to 0 very fast. So just because you end up with computing, because it's just because you end up with computing cosine of some number which is very close to 0, and this prevents the measure from being absolutely continuous. This is more or less the essence of Erdős proof. So we start.
Was a question also about if it is absolutely continuous, then the question about smoothness, density, and the speed of the decay is 0. Here it is bound away from 0.
Yeah.
No offense.
Yes. Okay. So this is Erdős argument. Okay, and so we let us, and this was already known back in 1940s, and Erdős, after proving this, he actually made a conjecture saying that if for almost every point the measure is absolutely continuous and its density is NA2 function, and this conjecture was proved by Solomiak much later, which brings.
Well, we said that Erdős proved it for lambda one. And the Solomiak extended this of the one half.
Okay.
And the idea is that there lambda k tends to integers, and there's proven that on the other hand, typical the sequence, the distance from integer is bounded away from zero.
Mhm.
That's why in absolute Fourier transform L2, so hence
Right. Okay, and so his idea that is he used, that's used by Solomyak, Mark Polypoitis and says claims that it is his idea, that it is the idea of transversality, saying that when you have that the fun that you can introduce, that you can use it as a parameter, and the functions has to be a basic choice of signs, and that it turns out to be that many functions are not very close to each other. And if the measure is singular, then a lot of functions which are comes from this parameterization by the choice of signs should be more or less the same. Okay, finally, yes. Maybe I will not go into that. I will take it as a homework, or I will send you some, or if you send me email, I will, otherwise I will not. Yes, maybe I will not go into that right now. Okay, so finally, in 2018, Schmort proved that if the set for which the measure is similar has Hausdorff dimension 0, so which is which is improved on the previous result by Solomyak. So in some sense, in this talk, we are interested in the parameter values where which form zero subset, measure zero set in all the space of parameters. Our interest is going to be in Hausdorff dimension of this measure. And what is that? So for simplicity, we can just define it, define the Hausdorff dimension of a set last time. So Hausdorff dimension of a measure is just infimum of the dimensions of the sets which have measure 1. And this quantity is called dimension of a measure, and this is the number we are after today. So it is convenient for us that the measure is actually exact dimensional. So that means that if you take the measure of interval and you divide it, logarithm of the measure of the interval, and you define it by the length of the interval, then in the limit you actually get the dimension. And I don't know whose result is it, but I think it is, so I just attribute it to the folklore.
This is, it's not clear who, but it is called Frostman.
The Frostman lemma, okay.
Yeah, there's a limit. Upper limit, then. It's one estimate of them.
Mm. And so our the question that we are bringing to is basically what can we say about Hausdorff dimension of Bernoulli convolutions. So I have to say that what we know is that the measure, the parameters when the measure is absolutely continuous, it's evidently the Hausdorff dimension of is 1 if the measure is absolutely continuous with the spectral event. So we are interested in parameters which, in the set of parameters which has 0 Hausdorff dimension. And one of the results in this respect was from Garcia from 1963, when he proved that if lambda is a Poisson number, then actually the Hausdorff dimension is strictly smaller than 1.
I'm not sure whether he really proved it. That's my idea. In fact, I proved it with Weiss about 1990. It's a student.
Okay, I have to double check that.
Of course, we use this.
Sorry about this. But then there was some exact estimates on Bernoulli convolution measure, which appeared in the 2002 paper, where they studied, where they considered the parameter values, which are the roots of this polynomial, and so that this. So all roots of polynomials like that, they in particular turned out to be Poisson numbers. They did the computations using the Garcia entropy, and what they currently conceive that, yes, of course, they are smaller than 1, but they are getting very, very, very close to 1 at the same time. So that's here for it's, and then that's like 1 10 minus minus 3. Things like this. And for this, we will need the notion that was in the heart of this computation. It is called Garcia entropy, if you want to look there. And the Garcia entropy is just defined in terms of the number of, you can consider partial sums. And what we are interested in, we are interested in the probability of getting the same number when you take the partial sum of our variables, of the partial sum of our power series. And then Garcia entropy can be defined by taking like the usual entropy, the way that you take a probability multiplied with the log of probability summed over everything. I'm not sure. So in some sources, the logarithm of lambda here is taken out, but I decided to put it in just so that I don't need to introduce 2 variables and only can introduce only 1 string. And a result by Hockman tells us that the Hausdorff dimension of the measure is a minimum between this quantity and 1. And also this result was only proved some years later. The essence of the computations, of the first computations, were in computing the Garcia entropy of corresponding to a particular, to this particular choices of Poisson numbers, and they rely heavily on the structure of the polynomial. So they rely heavily on the properties of these polynomials.
Let me comment. Garcia is the same Garcia who proved maximal periodic theorem. So this is Garcia's contemporary.
Right. Thank you very much. And finally, well, not finally, so that's Peter Varyu from Cambridge made a major breakthrough in 2018 when he proved that actually for all transcendental values of lambda, the dimension is actually equals to 1. Since then, I think his research group with his students maybe generalized, took it further to proving that if for many transcendental parameters, maybe under some extra conditions, the measure is absolutely continuous, but I have not read this much of it. And
We also commented there was a problem about Salem. So when these
this is
dual numbers to lambda have absolute values less equal. It is actually still open.
Yes.
Salem.
yes, the Salem numbers are still open. It will actually show up maybe if we get there. Okay, so and finally, then there was another result, but so that this leaves us with considering algebraic parameter values, and the same approximately time, there was a very short paper. It has only 4 pages, but it is standing on the shoulders of giant Schmerken, that they prove that Hausdorff dimension is bigger than 0.82. And establish this inequality between Hausdorff dimension for lambda and lambda squared. And we did it in a couple of years ago. We got the following uniform bound. We pushed it a little bit up. But we actually gave much more refined estimates. And 2 weeks after we put it on archive, another paper appeared from 2021. They put it to 0.92, and this is not improvable because it is the Hausdorff dimension corresponding to the parameter value, which is called Fibonacci. So the only thing I can say in my defense is that I actually learned about this problem when Benjamin Frank was talking about it in Cambridge in 2018. And they announced this result back then. So we somehow joined the race and we actually won by 2 weeks.
So this number is the infinum?
Yes. Yes, because in film it is bound, this bound is sharp. Okay, so our method is completely different to everything else, and maybe it can be used to, and it can be used for other iterated function schemes as well. So let me just try to explain it, but we also cheat. So instead of estimating the Hausdorff dimension, which is notoriously difficult, we work with another quantity that we found later in the literature under the name of correlation dimension. And it is in fact the maximal exponent, so that this double integral converges. So this is the integral of the difference between 2 variables in the square space. And it turns out that this correlation dimension gives us a lower bound on the Hausdorff dimension on the measure. This is and this dates back from energy principle, and you can find it in a book of O'Connor, for example. But the main point here is that it turns out that correlation dimension is much easier to deal with than the Hausdorff dimension. And in particular, what do we do? So we pick one number alpha, and our guess is that it is smaller than the Hausdorff dimension. And then you can, the function that defines this a double integral is actually continuous, and it is monotonously decreasing as at infinity. So this means for us that the stationary measure with our and since the measure that we are dealing with is stationary for so the iterated function scheme that we work with, it means that it satisfies this function that we introduce, which features in the definition of the correlation dimension. It actually satisfies this functional equation that which looks a little bit like magic at the moment. Let's just wrote it down for a particular case of Bernoulli convolutions. And in particular, when we saw this, we decided that we can introduce an operator acting on the space of functions, which does the following. It takes our function and assigns, to just take any function, in fact, and assigns the right-hand side to it. And this turns, and this operator that we introduced, the function, this one is just a fixed point for it. So the function which comes from the definition of the correlation dimension is just a fixed point of this linear operator, or not linear operator, it's just, we call it this diffusion operator, acting, linear operator acting on the space of functions. If this looks a little bit cryptic, let's just try gain. So we started with probability, so we are interested, so we can consider two variables distributed according to our measure, and we can associate the expectation, we can define expectation of the difference plus some number r, and we call this is our function, so it is just a shifted expectation of the difference.
So
yes.
Here, psi cubed as before, so psi cubed is the shift
Yes.
from. Okay.
Yes.
No. Is psi cubed as a shifted psi, or is it just?
No,
I think an independent copy.
Yeah.
It's what they say.
Oh, no. No, it is just yes, it is independent copy. Sorry. No, it's yes, yes. Sorry about that. Yes, independent copy, and then we can consider. And if you compute now this expectation, we just separate the first two terms, and then you observe that that the equality holds. That this is basically just the value of the function. This is a famous function phi evaluated at this new value. Which means for us again that in the language of probability, we can define an operator which takes a function and takes it to the expectation of the values of function, so an expectation of this random variable. Why is it good? Well, the good about it is that when we managed to prove the following fact, that if you have a random, that if you have any positive function, and it is nice enough, means that it is bounded from 0 and from infinity, and it is separated on the support of our interval mu lambda, and that it is decreasing again under action of our operator, then the parameter we have chosen is a lower bound on the Hausdorff dimension of our measure, and this is lower bound on a correlation dimension, and in particular on a Hausdorff dimension of the measure as well. And furthermore, these functions turned out to be relatively easy to construct. In particular, it is sufficient to look in the world of piecewise constant functions, and you will, if your guess of about lower bound on a Hausdorff dimension is correct, then you will find a piecewise constant function such that the inequality holds. So you may need to take smaller and smaller partition, but nevertheless, such a function actually exists. Yes.
To clarify, when you say everywhere on this interval, it means what can be this interval x or
X, yes. So the function should be defined on the interval which contains this interval as a subset, and in particular, so it is sufficient to be bigger than supremum of mu lambda. Yes.
so if for some fixed alpha lambda you have this, then you make conclusion that alpha less recurrent dimension.
Yes. Yes. We also produce a very nice algorithm for computing this function explicitly. Namely, it is just sufficient to iterate this operator applied to the indicator function. So this operator just it takes the minimum of the image of a function under the diffusion operator and the function itself. If you start with the indicator function, apply the diffusion operator, take minimum with what you had at first place, apply the diffusion operator again, take minimum with what you had, and then you proceed, and eventually you convert. You stop when you like, and then it converges actually to the. But it gives you a function which will satisfy this inequality. So here is a for example. For example, in the sense that so we started with a very simple function. It is 1 minus 1/5 of x. You pick up lambda equals to 0.25. And so this would be just this dotted lines. It is just a hat here. It's not really visible, unfortunately. But when you apply the operator to it, then you get this a bit curvy piecewise linear function, and we conclude that the Hausdorff dimension is bigger than 0.2. So we probably know this already because, but anyway, for the illustration purposes, this is what we're aiming to do. So we pick just any function that we like. We apply operator, we see that it got smaller, and we make a conclusion that the number we picked up is a lower bound on the Hausdorff dimension.
A question?
Yeah.
But I know actually for this case that the Hausdorff dimension coincides with the correlation dimension or fixed inequality?
It's an open question. So sometimes I think so. It says I think it is strict inequality usually. Like I don't, and moreover, we were in this case exceptionally lucky because they turned out to be very close. So in general, it is an open question, and I think even in this case, it is also an open question whether these two numbers are the same or not. Just nobody knows.
So your algorithm allows to obtain lower bounds on the correlation dimension.
Yes.
Can you obtain the upper bounds as well?
No, we tried.
I see. So you know in principle that you can obtain repeatedly well lower bounds, but we don't know
Yeah.
which point.
So, and the main advantage of this is that this approach doesn't really care whether number is algebraic, piezo, transcendental, or anything else. It is very easy to make it uniform. So if we want to consider an interval of parameter values, all we have to do is that you take the smallest lambda in your interval, take it to the power minus alpha instead of just 1 lambda to the power alpha. And here again, we just take the supremum of over all parameter lambda in our interval of the image of our function. So, and analog of the previous theorem still holds true. So if you find a function sufficiently nice, which means that it is separated from 0 and infinity on our interval here, and such that it got smaller under the action of this operator, then the number that we have found also a lower bound on a correlation dimension of alpha. So in particular, the estimates that we had, the results that we had before, they were applicable only as results for approaching the correlation dimensions, they were applicable only for selected values. And here, we actually can consider open sets, small open sets of parameter values all at once, which of course allows us to obtain estimates on the whole interval of the parameters.
Does it imply also semi-continuity of the correlation dimension with respect to lambda?
Lower. Let me think about it.
Okay.
Let me just not say anything silly. Let me think about it. And here is the same, also two example, but now a little bit more intricate. So we wanted to consider now just a small interval in the space of parameters. Here it is of the length 2 to the 10 minus 8. And for this, we built a function by summing up a lot of indicator functions, which is somewhere here. And again, the same approach works, that we apply our operator, we see that our function got smaller everywhere, fortunately for us, and we again make the same conclusion, but now on this parameter interval, the dimension is bounded from below. But in principle, the functions that we construct to like real in real life, they have infinitely smaller partitions, so they are piecewise constant functions. In reality, they are piecewise constant functions with about 10,000 intervals of continuity, and they look approximately, so here that's 120 intervals, which is still too much. So this is still too little. That in principle, this is how the functions look like. They are all this sort of bell-shaped curves. Okay. So using this method, we managed to obtain a very refined lower bound, which we could also improve further if we wanted to. But what we did, and here is a plot, So the statement of the theorem is a little bit, it's funny. It says that here is a function. It has 10,000 intervals of continuity. And it is, the graph of it is drawn like this. And this gives us a lower estimate on the Hausdorff dimension of a measure of the Bernoulli convolution for these parameter values. So here, of these biggest gaps, so we estimate only correlation dimension. We don't know how to approach the Hausdorff dimension itself. We still see that the biggest gaps seems to drop down. They actually correspond to the polynomials whose roots are Pizot values. So this, so all, and which we are able to identify exactly that. So there is some hope that we didn't, that our results match what one to expect. So that the dimension should drop when the parameter lambda is Pizot, and it actually does what it is supposed to do. So note here that it is goes from 0.97 and this is where it is achieved. It is tending to 1 when lambda is closer to 1/2, as one had expected. Then, if you go a little bit further, this is a continuation of this of the parameter lambda. Then here is this Fibonacci value. So our estimate is 0.96, while it is in reality 0.98. But for majority of values, we do quite well. Finally, you go further, and you see that the function is getting closer and closer to 1. And finally, if you go to the right parameter interval, it's getting almost flat, and it is actually above 0.99. And this is the last drop that we see, and this is also the last Pizot number, this is the polynomial, it's the biggest Pizot number. Finally, and what we can say that in addition to this, we did something more than that. We can consider we can consider other linear iterated function schemes, but we get much weaker result. So using sort of similar approach of diffusion operators, we can also give an estimate on something of this parameter alpha, which is sometimes called Frost-Von exponent. It's a lower bound on the correlation dimension, and that maybe it is it might be useful if there is nothing else one can do. So that's basically it. I think I'm almost on time.
So, do you think it is possible to improve this method to detect absolute continuity for some parameters?
Absolute continuity? I don't think so. We can so that like if even if the dimension is one, it doesn't really mean that the measure is absolutely continuous. So for absolute continuity, there is some. I was checking what Peter Wagner with his research group was doing recently, and there is a very new paper by one of his students where he deals with absolute continuity, but what he's doing, he's building on approximation of, or he's studying Garcia entropy, and he's considering questions how Garcia entropy, which we have seen, depends, changes along the sequence. So like if you take, for example, transcendental value and you approximate it by a sequence of algebraic values, and he's studying how Garcia entropy changes along these sequences. And yeah, so it is very evolved, but they are doing something different. So that's no.
Not directly related to your development here, but do you know what the dimension of the set of these zoning is?
Which dimension?
Box dimensions in this countable set. So which would make discuss about
Of Poisson numbers. I'm afraid I don't. Maybe somebody else knows more.
To have this distribution, the graph, and then you project it to the. So question is, what is Hausdorff dimension of the graph? Is it the same as box dimension or not? Box dimension will be easier. I need this function plus minus number. Plus minus another. Maybe a question about box dimension. Type just for both dimension of the graph. But it's easier to say what it is. Hausdorff dimension of sometimes for this. And we reduce it. That is projected the graph.
maybe this is something that this could possibly tell you the box dimension of the set of Peele numbers.
No, I think both dimension for the probability distribution doesn't make sense.
No, this set of
Our dimensions need to be known.
it's not like directly related to the techniques here, but this came up in 2016 at another. It's no one curious if there's been any developments for these.
Is there any thoughts about the amount for the dimension when lambda is lesser than 1?
Even the dimension of a counter set, it is self-similar.
The house of the measure you want.
Yeah, you can see a second.
No, because for lambda bigger than half, there's the first 2 years ago distribution.
Yes, we go around who is in this is talking about the one.
For example, when lambda was less than half, right?
No, so when lambda is equal to the half, you get the counter set, and the measure is supported on a counter set, and that's
Again, the box in this case, the box dimensions is special. Yes, then it makes sense.
Yeah. But the counter set has zero Lebesgue measure.
Or because how to question.
And then if you're not there, is it absolutely continuous with respect to the Hausdorff measure?
I have to say that that's
When you compare with the data, right? Then you can ask if you are in a counter set, there is no counter set, whether if you have the right dimension, are you absolutely continuous with respect to the Hausdorff measure?
The same kind of question as for lambda.
Sure. I will.